In this lesson, we explore polynomial equations that have imaginary and irrational roots. We'll use clear examples, solve them step by step, and visualize why these roots make sense. Let's start with irrational roots. Consider the equation x squared minus 2 equals 0. This is a polynomial with no integer roots, but it still has real roots. We solve by isolating x squared. Add 2 to both sides. So x squared equals 2. Then take the square root of both sides. The solutions are plus square root of 2 and minus square root of 2. These are irrational numbers. To visualize those roots, we can place them on a number line. Square root of 2 is about 1.41, and negative square root of 2 is about negative 1.41. Now, let's look at imaginary roots. Consider x squared plus 1 equals 0. This has no real solution because x squared is always non-negative. Solve it by isolating x squared. We get x squared equals negative 1. Taking square roots gives x equals plus I or minus I, where I is the square root of negative 1. These are imaginary roots. We can represent imaginary numbers on a simple vertical imaginary axis. The point I is 1 unit above the origin, and negative I is 1 unit below. A quick way to predict the type of roots is by using the discriminant from the quadratic formula. For ax squared plus bx plus c equals 0, the discriminant is b squared minus 4ac. If the discriminant is positive, we get 2 real roots, often irrational. If it is 0, we get 1 real double root. If it is negative, the roots are imaginary. Let's summarize. Irrational roots appear when the square root does not simplify, like plus or minus square root of 2. Imaginary roots appear when the square root involves a negative number, like plus or minus I. Both types are common in polynomial equations and are fully valid solutions.
Welcome! In this video, we'll learn the relationship between roots and coefficients using symmetric functions, and then see how transformations of equations move the roots. Let's start with a quadratic equation. Consider a general quadratic equation. We write ax squared plus bx plus c equals 0. If the roots are r1 and r2, then the polynomial can be factored. It becomes a times x minus r1 times x minus r2. Now expand the factored form. We get ax squared minus a times r1 plus r2 x plus a times r1 r2. Since this equals ax squared plus bx plus c, the coefficients must match. This gives 2 key relationships. R1 plus R2 equals negative b over a, and R1 R2 equals c over a. These 2 expressions are called symmetric functions of the roots because they do not change if we swap R1 and R2. The sum and product are the most important symmetric functions for quadratics. For a cubic, the idea is similar. Suppose the roots are R1, R2, and R3. The factored form is a times x minus r1 times x minus r2 times x minus r3. Matching coefficients gives the symmetric sums. Now, let's see how transformations move roots. If we replace x with y plus h, we are shifting the graph left by h, and each root shifts by negative h. So if x equals r is a root of the original equation, then y equals r minus h is a root of the transformed equation. Let's do a quick example. Suppose we have x squared plus 6x plus 5 equals 0. The roots are negative 1 and negative 5. If we set x equals y minus 3, we shift right by 3. The new roots become 2 and negative 2. The transformed equation becomes y squared minus 4 equals 0. Summary: the coefficients of a polynomial are symmetric functions of its roots. For quadratics, the sum and product of the roots match negative b over a and c over a. For cubics, the symmetric sums match b, c, and d over a. And when we transform x to y plus h, every root shifts by negative h. Thanks for watching.